In this video, I want to prove to you that if a graph has no odd length cycles, then the graph is 2 validly colorable, so 2 colorable. So if a graph has no odd length cycles, then the graph is 2 colorable. So how is this going to work? Well, let me show you an algorithm for coloring a graph. So I'll give you an algorithm for coloring a graph, and then we'll prove that this algorithm works assuming no odd length cycles in the graph. Okay, so that will prove the claim. So the claim says if a graph has no odd length cycles, then it's 2 colorable. How are we going to prove it? I'm going to give you an algorithm for coloring a graph using 2 colors, and then we'll prove that this algorithm actually works assuming there are no odd length cycles in the graph. So if there are no odd length cycles, then this algorithm for 2 coloring a graph will work, and so the graph will be 2 colorable. Okay, so what's the algorithm? Well, it works as follows. So we have some graph. Let's say that's our graph. We'll fix some vertex v. Let's call it this vertex v. And every vertex that's odd distance from v, color white. Okay, so every vertex that's an odd distance from v will color white. I'll tell you about distance in a second. And every vertex that has even distance will color black. Okay, and what is distance? Distance from u to v is equal to the length of the shortest path from u to v. Okay, so for example, v, so every distance that has even distance from v gets colored black. So v has distance 0 from v, which is even. So v is colored black. Okay, and let's look at this vertex. Let's call it w. The shortest path from v to w has length, well, 1, 2. So that's even, so it also gets colored, so w gets colored black. Let's look at this vertex. Let's call it x. What does x get colored? Well, it's of odd. The shortest distance from v to x is 1, which is odd, so this gets colored white. How about this vertex? Its distance from v is 1, 2, 3. That's odd. It'll get colored white. This vertex over here, the shortest distance is 1, 2, 3, 4. So it gets colored black, and so on and so forth. As you can see, this coloring will assign a color to every vertex in the graph. Now, how do we prove that this algorithm actually works? Okay, well, so we need to prove that if G has no odd length cycles, it implies that this algorithm works. Great. So let's do a proof by contradiction. Let's assume, by way of contradiction, that the algorithm fails. What does this mean? It means that there are two vertices in the graph. Let's call it x and y. And let's say, v, that initial vertex that we chose, is sitting over here somewhere. It means that there are two vertices, x and y. They're connected by an edge, but they both got colored, let's say, white. If the proof is the same if they both got colored black. So we can say, without loss of generality, let's assume they both got colored white. Remember, we're doing a proof by contradiction. We're assuming the algorithm fails. That means that there are two vertices that are connected by an edge, and they ended up getting the same color. It's a failed coloring. Okay, well, if x got colored white, it means that the shortest path from v to x had odd length. Remember, everything that gets colored white has odd length. If v to y, maybe it starts here and then diverges. If v to the y, if y got colored white, that also means that the shortest path from v to y had an odd length. Notice we've created a circuit, not necessarily a simple circuit or a cycle. We've created a circuit in this graph from v to x, take y, and then trace your steps back on this path back to v. Okay. What's the length of this particular circuit? So let's write this down. So this implies there exists a circuit, basically that starts at v, goes to x, takes y, and goes back to v. And what's the length of this particular circuit? Well, it was an odd number of edges to get to x, plus 1, so that's even. And then even plus an odd is odd. So the whole length of this circuit is odd, right? Because we colored x white, we said x was white, y was white. That means that the shortest path from v to x is odd. That means there's a shortest path from v to y that's odd. And so there's a circuit that goes v, x, takes this edge, goes back here to v. So there's an odd length circuit in this graph. What do we know about odd length circuits in graphs? We've proved in a previous video. This implies that there exists an odd length cycle in the graph. Well, great, our proof is done. Remember, we said that we assume that if G has no odd length cycles, then the algorithm works. So we did a proof by contradiction. We assumed that the algorithm fails, and we ended up concluding that there was an odd length cycle in the graph. But we assumed that G has no odd length cycles. So this is a contradiction. That means that the algorithm works. And that means that if the graph has no odd length cycles, then this algorithm actually two-colors the graph. So we proved that if no odd length cycles, then it's two-colorable. And in the previous video, we proved that if a graph is two-colorable, then there are no odd length cycles. So we've just proved that having no odd length cycles is equivalent to being two-colorable.